Hello, in this series of videos we are going to introduce the reactions of alcohols. Alcohols are hydrocarbons that exist in our daily lives. It can have multiple reactions with a variety of chemicals, and it reacts mainly by its functional group, hydroxyl group. Alcohols have 5 main types of reactions. First is dehydration, second is oxidation, third is reaction with hydrogen halides, fourth is reaction with phosphorus halide, and the fifth is esterification, which will not be included in this series of videos. Before we learn through these reactions, we should learn some basics of alcohols first. There are 3 types of alcohols: primary alcohols, secondary alcohols, and tertiary alcohols. Primary alcohols refer to alcohols that have one carbon atom directly attached to the carbon atom, which is attached to the hydroxyl group. Propane 1-nol, ethanol, methanol are the examples of primary alcohols. Secondary alcohols refer to the alcohols that have 2 carbon atoms directly attached to the carbon atom, which is attached to the functional group. Propane 2-nol, butanol, cyclohexanol are the examples. Finally, tertiary alcohols refer to, you guessed it, the alcohols that have 3 carbon atoms directly attached to the carbon atom, which is attached to the hydroxyl group. Examples like 2-methylpropane 2-nol and 2-methylbutane 2-nol are tertiary alcohols.
Let's begin with the dehydration of alcohols. The principle of dehydration is extracting water molecules out from the alcohols. Alcohol can undergo dehydration in 2 different ways. Let's take ethanol as an example. The first way needs to be done in the presence of excessive concentrated sulfuric acid, which will act as a catalyst and in a relatively high temperature condition, around 180 degrees Celsius. As we said, dehydration is taking water molecules out, so the products will, of course, include water. During this reaction, the OH group from the alcohol and the H atom from an adjacent carbon atom in the same molecule will be extracted to produce water. The bond electrons they left will form bond with each other. Thus, the other product of this reaction is alkenes. Since the temperature is at 180 degrees, water will vaporize and leave the alkenes alone. If there are excessive amounts of ethanol stored in a 140 degrees Celsius room, the alcohols will go another way to dehydrate. By this way, the whole OH group of a single molecule and the H atom of the OH group of another molecule will be removed as water. The 2 ether groups will then attach to the oxygen atom to form an ether molecule. Once again, since the temperature is at 140 degrees, water will vaporize and leave ether alone. These are the 2 ways you can dehydrate alcohols.
Now, let's take a look at the oxidation of alcohols. We have learned that oxidation is increasing the number of bonds of oxygen atoms and removing hydrogen atoms. In primary alcohols, there are 2 hydrogen atoms can be removed around the functional group attached carbon atom. So, primary alcohols will undergo oxidation 2 times when they face oxidizing agents such as acidified potassium dichromate, acidified potassium permanganate, and so on. For the first oxidation, the hydrogen atom of OH functional group and one of the hydrogen attached to the carbon atom will be thrown away. Then, the electrons they left will form bond with each other, and thus the primary alcohol becomes an aldehyde. For the second oxidation, an oxygen atom will be acted in between the carbon atom and hydrogen atom, and thus the aldehyde will become a carboxylic acid. In secondary alcohols, there is only 1 hydrogen atom you can throw away, so it can only undergo oxidation 1 time. Like primary alcohol, the hydrogen atom in the OH functional group will be detached, and the hydrogen atom attached to the carbon atom will be thrown away also. Thus, the secondary alcohol will become a ketone. What about tertiary alcohols? Well, things go pretty differently in tertiary alcohols because there is simply no hydrogen atom you can throw away. So oxidation cannot undergo in tertiary alcohols.
Next, we are going to have a look at the reaction of alcohol with hydrogen halide. When alcohols are brought nearby hydrogen halides under strongly acidic condition, substitution will occur. That means the alcohols will come out as haloalkene after a series of reactions. The reactivity decreases from tertiary alcohols to primary alcohols. Before talking about the reaction, we need to know what reflux is. Reflux is a system that built to reduce the amount of chemical loss by evaporation while heating. Let's say you want to heat the water into 90 degrees. It is impossible for the water to not vaporize because the temperature you want is so close to its boiling point. So, this setup is introduced. Once the water evaporates, it will rise to the condenser part, and thus will be condensed back to water droplets and reflux back to the flask. Alcohols evaporate easily, so reflux is very useful when it comes to heating alcohols. Now, let's take a closer look at the reactions. For hydrogen fluoride, it is generally unreactive, so there are no reactions between alcohols and them. As for hydrogen chloride, the reaction can undergo by two ways. The first way is bubbling dry hydrogen chloride gases through the mixture of anhydrous alcohol and anhydrous Sin2 chloride, which act as a catalyst. The second way is refluxing the alcohol with concentrated hydrochloric acid in the presence of Sin2 chloride as catalyst. These reactions will give haloalkene and water as products, but if the alcohol you are using is tertiary alcohols, you will see the reaction right after you have added concentrated hydrochloric acid in. This is because the reactivity of tertiary alcohols are so high that it doesn't require a catalyst. For hydrogen bromide, you need to have a mixture of alcohol, concentrated strong acid like sulfuric acid and metabromide put into a reflux setup. For example, if you want to see a reaction between propanol and hydrogen bromide, you need to put propanol, concentrated sulfuric acid, and sodium bromide into the round bottom flask of the reflux setup. When you heat it up, two reactions are undergoing in the flask. First, sodium bromide will react with sulfuric acid and gives sodium sulfate. And more importantly, hydrogen bromide. The hydrogen bromide will then react with propanol and gives bromopropane and water. Lastly, we will use a distillation setup to separate out the bromopropane. This is the reaction between alcohols and hydrogen bromide. Similar reactions will happen between alcohols and hydrogen iodide.
Now, let's go through the reactions between alcohols and phosphorus halide. Their reactions are very similar to hydrogen halide. Once again, phosphorus trifluoride will not react with alcohols because it is stable. For phosphorus pentachloride, it will react with the alcohols once you drop it in under room temperature. The reaction will give haloalkane as one of its products. For phosphorus tribromide, you will need to add red phosphorus and bromine solution into the alcohol, then heat them up in a reflux setup. The phosphorus will first react with bromine and give phosphorus tribromide. The phosphorus tribromide will then react with alcohol and give bromoalkane as one of its products. You can put the mixture in a distillation setup in order to separate the haloalkane. A similar reaction will happen if you replace bromine solution into iodine solution.